G'day you mob, and welcome to this episode of The Goss. I am your host Pete, and this is Aussie English, the number one place for anyone and everyone wanting to learn Australian English. So in this episode of The Goss, guys, I sit down with my dad and I talk all about how to clone a dinosaur. So we've all seen that movie, at least I assume, Jurassic Park. I think it came out in 93 when I was a little tacker. I think I had it's probably like 6 years old. Very young kid, but I love that movie. Absolutely fell in love with dinosaurs and them extracting DNA of the dinosaurs out of amber, out of the insects that were trapped in amber, and then creating this crazy park where all kinds of stuff goes wrong. Anyway, since then, it's probably been, 27 years, there's been lots of debates about whether or not this would be possible to extract DNA of anything out of amber. Today we talk about that, and then what you would actually need in order to be able to clone a dinosaur if it were possible. And then also the future of computing large data systems and what that could potentially mean for biology, ecosystems, genetic engineering, cloning, everything like that. So without any further ado, guys, smack the bird. Let's get into it. All right, tally-ho, what's the next one? You got heaps today.
No, I think that I'm just about out, I think. Hang on. No, the others were my... the breaking news has sort of disappeared. There's a whole lot of crap in there now that's just COVID. So,
yeah.
Yeah, the only thing that you talked about earlier about COVID is that now New South Wales has more active cases of COVID per day than Victoria.
Who's laughing now, guys?
Yeah, well, yeah. But
you poke fun at us.
Yeah, we're still in the sort of, the single digits or low teens. Yeah. But and that has increased the pressure on Daniel Andrews, the Premier of Victoria, to reduce the restrictions, where they're saying, look, Victoria's now potentially in a better position than New South Wales, and New South Wales doesn't have anywhere near the restrictions of lockdown that we do. So
it's such a hard game to play. I can't imagine being a leader in that sort of a position.
It's a lose-lose no matter what happens.
Yeah, because I think Britain's in that position too, where Boris Johnson is currently faced with having to decide whether or not to lock down the place. And I think the doctors just told him, numerically, if you lock down for just 2 weeks, you'll save 7,000 lives by December. Yeah. And it's like, what do you do in that situation where you are effectively fighting people's short-term versus long-term interests? So I'm sure the average Brit is thinking, screw that, I don't want to have to deal with that. But if you said to them, all right, your grandparents die, or you're one of the 7,000, I'm sure they would change their mind. So, I don't know what you do in that position, but I can't imagine. Dan Andrews, how many days in a row has he been working now? He must be like, I'm just so over this.
He hasn't had a day off since last year.
Yeah.
Because he was, with the bushfires that started in December.
Jesus.
In Victoria.
Yeah.
They started earlier than that in New South Wales and Queensland.
Going from September, October, wasn't it?
Exactly.
And we're all of a sudden, I remember we were talking about that in the first Goss episode, or second one. Yeah. And now we're back to the same season, bracing for that to happen again.
Yeah, well, fortunately, we've had a wet winter and early spring in eastern Australia.
And the bushfires from last year, which probably cleared away.
Well,
a lot of the
one
fuel.
Good thing that comes out of those is that it blows out the fuel for the next few years. But we've also had a wet year, which has been good for two reasons. One is obviously it's broken the drought in northern New South Wales and southern Queensland, and there's just been more rain around, so there's not the amount of dry material around. So.
Do you remember that ad that was for? I think it was for corn. And there's this guy sitting on his old Outback station house in his chair on the deck, looking out, and it's just like really dry, and there's dust everywhere. The tumbleweeds are blowing past, and he starts hearing rain.
Tumbleweeds in Australia.
Yeah, exactly.
Yeah,
you know what I mean?
Yeah,
probably was in the ad.
Yeah, exactly.
But rain starts falling on the roof, and you hear him yell out that, Marge,
yes.
The rains are here. And then it's like the shot zooms out and reveals there are two kids out at the top of the house eating corn outside of the window, and the whole point of the ad is the corn's so juicy, all the water's like falling onto on the corrugated iron roof. I remember that ad.
Yes, I do.
I had a good story here that was talking about for the first time, scientists have successfully extracted DNA from insects embedded in tree resin. So this is sort of reminiscent of the idea behind Jurassic
Park, isn't it? Yeah.
Which is, for anyone wondering, complete BS in terms of it's not possible.
Sorry to remove you from that, but there was a really good documentary made a few years after Jurassic Park, which went through they claimed there were 7 steps that needed to be taken.
Jurassic Park did, or the scientists
said there were 7 things that needed to happen in order for Jurassic Park. The concept of recreating an animal out of DNA that had been trapped in resin, and they went and debunked each of the 7 as to why, under current technology and understanding, it couldn't happen.
Yeah.
So it was a really interesting one, but that was 20-something years ago.
Well, I imagine you would have.
I mean, you're a DNA gene jockey. I'm not.
You need the dinosaurs there. You need a mosquito or some sort of an insect to have consumed DNA or biological material from those dinosaurs. You need that material to have survived inside of the insect intact, which you would assume is potential, but it's not going to be very long. You would imagine it's going to get digested and broken down pretty quickly. And then you need it to land on a tree where the sap's coming out. You need the sap to completely cover the animal and for that to be then saved by falling onto the ground and becoming fossilized.
Yeah.
And then for you to find that. And the problem is, I think, too, you need the DNA to survive inside of the amber for millions, tens of millions, hundreds of millions of years, right? More than 65 million years.
70 million years, but...
Which is an impossibility, I think, at least as far as we know. And that was what this study was sort of looking at. They had trouble getting DNA out of these small beetles that had been covered in resin 2 to 6 years ago. So the samples are being collected and stored for 2 to 6 years. And the study had all these issues. I think they were first trying to use ethanol to dissolve the amber, and that was affecting the DNA. Then they had some issues with the polymerase chain reactions, the PCRs that they were using to try and amplify the DNA. These are all very technical terms, but to sort of break that down, a PCR is... this is hard enough to learn after you've finished a master's in biology, but...
Try explaining it to layperson's
You
terms.
extract DNA from the cells of an organism, whether it's a plant or a human, so you can effectively put it through a cooking process that takes the DNA out of the cell. It separates it itself out so that you end up with pure DNA, except that it's chopped up and fragmented. And the PCR, what the PCR does is split the double helix of DNA and then replicate it by copying each of those individual strands and turning those into 2 more double helix strands that they can then divide and then replicate.
Yeah. And so the genius in that was the guy, and it was a guy in Melbourne who invented it.
Sanger sequencing,
which was that you're using a particular bacteria to allow you to do it initially, and they could turn it on and off just by raising and lowering the temperature.
Yeah.
And so every time they raised the temperature, it stopped. They lowered the temperature, it started. And so they could just multiply these replications just by raising and lowering the temperature in the
lab. And to sort of go on a tangent, this is how I imagine they're doing all of these COVID tests. What they'll actually be doing is taking people's genetic samples effectively, so swabbing their mouths or their nose, pulling out whatever's in there in terms of viruses, and then denaturing the DNA, pulling it apart, sucking it out of the sample, amplifying, and then, putting it through a PCR process using what we call primers, which are certain small coded things that we've made, sequences of DNA that we've produced that only latch on to specific areas of DNA from a certain organism. And only if they find that DNA present in these samples will they replicate, and then you can test and see, there's that sequence in this sample, so that means the DNA of this organism was in that sample. And so that's what they're doing for the COVID test. They'll just be PCRing it and then seeing is there a presence absence of COVID virus DNA. So it's a pretty cool test because it's just so quick. It takes 30 minutes for you to run a PCR where it's just the temperature is going up and down and causing the DNA to come apart, to get replicated, to go back together, to then come apart again, replicate again, and each time it just goes up obviously exponentially. And then after that you just test, you say, what do we have the presence of any of these samples we were chasing with those little primers, the scissors looking for that DNA. But the the reason that it's so difficult is that DNA has a half-life of 521 years. So that we like to think, when we talk about the genome, so that is all DNA in an organism that codes for proteins. Well, I guess it's the entire, what would you call it? The entire protein chain.
Yeah.
It's not a single chain. It's many, many different ones. All of your chromosomes are effectively individual chains. So you've got, 26 of them or whatever it is. 23 of them, yeah. I should know this better than you.
You worked on rodents. They have hundreds and hundreds of chromosomes.
No, dozens. But they break up. And so you don't actually have a single strand of DNA. You've got many.
Yeah.
And then when it's taken out of you...
And most of it's junk anyway.
Yeah, but when it's taken out of you, it starts breaking into smaller and smaller parts. And so every 521 years, like uranium, right? If you've got 1,000 atoms of uranium in whatever it is, tens of thousands of years, it's 500 and then 250 and then... Yes. Until to the point that there's nothing left. It's the same with DNA, where if you had... strands that are hundreds of thousands of base pairs long, in 520 years, they're all half that length on average. In another 520 years, they're half that length again until you get to the individual components. And then you would imagine they just break down into atoms. And so the reason that we could never get dinosaur DNA out of something that's a fossil is because even if the DNA was there, it would be broken down so far that you would never be able to reconstruct the actual sequence, the actual DNA, the genome of the animal. You would just have, the individual parts and the pieces of the jigsaw, and you wouldn't know how to put it back together. And so that breaks down within, I think it's like 500,000 to 1 million years. That's sort of the max.
Just disappeared. Gone.
Yeah, after that point, there's just nothing coming out of it. And I had that sort of trouble with specimens that were preserved that were only 120 years old.
Yeah.
Although these were museum specimens I was trying to get DNA out of to compare them to, contemporary individuals from those species or extinct species. But even that was difficult just because the conditions that certain samples are kept under can degrade the DNA further with sunlight, with, arsenic and other things that are put onto the specimens that destroys it as well.
Yes, because when those samples were being taken, they were just trying to keep the skins, the pelt and the fur, and the skeletons. They weren't trying to retain DNA.
They had no idea.
They didn't understand what DNA was. So, and even 50 years ago when people did understand what DNA was, I don't think they were, contemplating the importance of retaining good cell structure so that you could get complete bits of DNA. They were just saying, well, let's just fix this, because really what they wanted was the skeletons and the skins.
And when you say fix, you mean...
Fix as in...
Not repair.
Not repair, as in stopping any degradation, breakdown after it's
treating it in some way
treating it with all
bugs
sorts of
or other things
chemicals.
aren't going to eat them.
Yeah.
It is an interesting field of study, though, and the most interesting stuff, I think, comes out of... places like Siberia, and caves in Australia
frozen.
Where you find megafauna that are this maybe tens of thousands, hundreds of thousands of years old, and there is still the possibility to pull the DNA out of those things. And I mean, there are people who want to clone the woolly mammoth and the rhinoceros and even the thylacine.
Yeah.
And if that ends up happening, it will rely on being able to pull out intact, high-quality DNA from specimens that are hundreds to potentially tens of thousands of years old. And then not only just being able to get the DNA out, but being able to somehow reconstruct it into something that is biologically feasible.
And that's what a lot of that documentary on debunking that whole Jurassic Park story was about. Each of those steps from, even if you assume you can extract bits of DNA, each of the steps to go from there and to producing a living organism out of it was really interestingly done. It was an hour of really cool science.
Yeah.
And it was one of those things where they were explaining why you couldn't do something with science rather than why you could, which was an interesting way of looking at it.
You wonder what the difference is going to be once we get enough computing power and algorithms and AI.
So you can rebuild.
I think you'll be able to rebuild anything. You'll be able to create anything because you'll effectively have an algorithm or AI that can run so many tests virtually in the, instantaneously to do enough tests to be like, what happens when the DNA is this coded? What happens? And so it just needs to go from, you know, if a bird has come from, evolved from dinosaurs, the machine just needs to work out how do we change the bird's DNA to create something that is viable that is the shape and size and appearance of a Tyrannosaurus Rex. And you would imagine, you know, it's just a matter of computing power.
Yeah.
That I think if you can work out the way to run enough tests on having a viable animal like that virtually, then you just have to be able to clone it somehow once you've worked that out. So
yeah, I think that's talking about something that's millions of years old. The other aspect that would be more appropriate, I think, in terms of relatively recently extinct things. You're talking about the thylacine, which the last one of those died just under 90 years ago.
1935, I think.
But there will be thousands of samples, biological samples, sitting in museums, and each one of those might be degraded, so you can't do it. But once you've got that computing power that just says, we'll take all of these things, and then they can start matching up. And you go, well, we get this much from this one, and then we get that little bit from that one. So there's a bit of overlap. Now we know that those two bits there, so we add those together and we've got that. And you just keep doing that until you can reconstruct all of the chromosomes.
Well, and the interesting thing beyond that would be, how do we then insert, if you get it down, okay, we can put together a genome of a thylacine. We can then clone it by effectively inserting that genome into a blank egg of the closest living relative, you know, a quoll or something, or a wombat or Tasmanian devil, so that it effectively, you know, gives birth to a thylacine.
Yes.
All we need after that is to work out how do we insert diversity, genetic diversity, into that population. We don't want just the same individual thylacine replicated the whole time, because it'll go extinct straight away again, you know, from other problems after a few generations. It'd be like me having children with myself, if that were possible. The next thing will be having the computing power to work out how do we add differences in the genome, in the DNA, that won't be deleterious, that won't cause any negative side effects, and will effectively fast-tracking evolution itself, because, you know, natural selection would weed that out. But it'll be interesting to work out if computing power can ever do that, both for extinct animals and animals that are going extinct. Because if you could just suddenly be like, we can digitally come up with genetic diversity that we can then insert into embryos and insert that into the animal, and then those animals will have, you know, so much diversity that if they were to interbreed, they're not going to have genetically deformed things, congenital diseases and other problems.
Or if the environment changes slightly, then there'll be enough diversity, so there'll be some individuals that'll survive.
Because you can imagine, again, it's just a question of computing power that's holding us back.
Without doing it artificially, there must be a lot of research going into that with severely endangered species. Think of the orange-bellied parrot, which got down to a handful of breeding pairs. And, then there was a breeding program, several breeding programs in captivity to release them back into the wild. There must be an enormous amount of tracking diversity in those, so that you are trying to crossbreed with as diverse a population as possible, rather than going, well, these are the two super birds, we're going to breed everything from them, which means that you get all of them after that become super birds. But then if anything changes, or you get suddenly go, oops, there's a few little mutations in there that, when you put two and two together, you get dead.
Well, that's kind of the problem we're facing, though, right? Where we're at, I don't know if the science says we're in a mass extinction event or not, at least based technically on the definition of the term.
Yes.
I assume that we are, though I don't know how you define it and what the criteria are.
The problem we have, just to interrupt you with that, I think the problem we have with that is that we have retrospectively loosely defined a mass extinction event for things that happened millions of years ago, or at least tens of thousands of years ago in some cases. Whereas what we're looking at now are things that are happening in decades, not in over thousands or millions of years. So, it's hard to define, what the number, of the loss of a particular number of species in an area in a year or 10 years. Is that a mass extinction, or is that just a blip in the radar, or is it something worse?
But it is interesting to think about what humanity will be able to do in the future once once and when and if we get this sort of technology, assuming we get through COVID and the world pulls through and keeps advancing technologically.
Ironically, I think there's been more money put into DNA research in the last 6 months than there has been in the 6 years before that, because as you've already identified, a lot of the identifying the virus is about understanding its DNA, and that's easy to do. But then trying to find solutions to that, most of those are about manipulating DNA in various organisms and or the virus itself that will allow us to create either a treatment or a cure. And so it's a huge amount of effort going into just understanding viral DNA, which has got to pay off in other areas eventually.
Yeah, but I wonder what we're going to be able to do in terms of rejuvenating the world's habitats and, ecosystems after we destroy them, because at least at the moment we think when they're gone forever. But you wonder at what point that won't be true, because we'll have surpassed a certain technological limit that will allow us to use technology to repair ecosystems. Because again, you imagine it's just a question of data, computing power, and technology in terms of, cloning things and being able to do it.
Yeah.
And it'll be crazy. But moving on to the COVID and the virus, you wonder, looking back at, say, World War II, I think we see that war was horrible. Hundreds of millions of people died, but we got things like the jet engine out of it. And I think... and a lot of surgery that came out of it from, I think most surgery was actually improved because of wars, both directly and indirectly, because you had so many people maimed all the time that doctors could just willy-nilly have to try new things to try and fix people and help them survive. You wonder what's going to come out of the amount of effort and resources that we're currently putting in against COVID, the virus. I mean, not just what we'll be able to do in terms of dealing with COVID, but are there other technologies and things that are going to come out of all the billions of dollars that we're currently throwing at this issue? Because we don't know if it's going to last for 4 or 5 years like the Second World War. It could keep going for the rest of our lives. But you would imagine that there's going to be certain advances that'll be made here that are probably unforeseen, that may not have anything to do with viruses in the future.
Yeah. Well, Spanish flu is a good example of that. 100 years ago, killed more people than COVID has currently killed around the world, when the world had a much smaller population. But from that, people started working on developing a greater understanding of what influenza was and creating vaccines for it.
Yeah.
We still have tens of thousands of people a year dying from influenza. But we can save millions of lives a year because we have a vaccine for it. And I think the same thing will happen with COVID. It's just another form of a flu virus. So we'll eventually come up with vaccines for that and we'll save them. But lots of other things have come out of that as well. We understood a whole lot more about vaccines with flu, because the original vaccines that were coming out for things like smallpox and so on were smallpox is a very complex organism in comparison with the flu virus. And so it mutates. It's an old, ancient thing. It's large. It's complex. It mutates very slowly. And so a smallpox vaccine worked for 100 years.
Well, to pause you there, the vaccine for smallpox originally used to be that they would pick the scabs off the pox, and crush them up and get you to sniff them or scratch it into your body.
Yeah.
And so you would just get effectively a small inoculation of it.
Yeah.
All right, guys, thank you so much for joining us. Me and Noah, he's here as well, smacking the microphone with his spoon. That was another episode of the Goss. Don't forget, guys, if you want to get access to all of the Goss episodes, the transcripts, the MP3s, the videos, the entire episodes from 1 to, I think we're up to like 40-something now. Yeah, that's it, mate. Just go to aussieenglish.com.au and you can sign up for those. Anyway, I'm Pete, your host. This has been another Aussie English episode. It's a pleasure, and I'll see you soon.